Course Chemistry, and welcome to Chapter 13, Section 13.8, where we are going to talk about how we can take the concept of molarity from Chapter 13 and tie it back into what we learned in Chapter 8, which is reaction stoichiometry, right? We have the concept of mole ratio, right? Remember, and those come, mole ratio, which comes from our balanced equations, right? Those are the coefficients from our balanced equations. We also have the concept of molarity, which is moles equal to 1 liter, right, of solution, and specifically moles of solute. And in the land of conversion factors, we also have things like molar mass, right, which we've been using a lot. So that's in moles. Let's say the number of grams equal to 1 mole of a given substance, right? And here is where, as long as we understand the definitions, it helps us to make sure we write it correctly, right? Some of you guys have asked about, well, how do I know if I should incorporate the coefficient when I'm doing the molar mass? Well, the definition of molar mass is the mass for 1 mole. So clearly you wouldn't incorporate the coefficients, right? This is where the definitions are important. So we have mole ratio, molarity, molar mass, right? Don't forget we've got other things like density, for example, right? Which is the number of grams equal to 1 unit of volume, typically a milliliter, but it could be a liter, right? Or centimeter cubed, or any volume really, right? We've got, what else? Right. We've got Avogadro's number, which gives us the 6.022 times 10 to the 23rd particles equals 1 mole, right? And so we've got all these conversion factors that we know, right? And so basically you guys know a lot of chemistry, right? All right, let's do some practice. So this one says, how many milliliters of this solution? So we want to know the number of milliliters, which is a volume, of this molarity, right, will completely react with this volume and this molarity of that substance according to the reaction, right? So if there weren't a reaction written, clearly a clue to you would be that, oh, here we have one chemical compound, here we have a different one, right? Which makes this different from M1V1 equals M2V2, right? Because at first glance you might be tempted to say, oh, I'll just do, this is just a dilution, but it's not, right? This is not a dilution because these are not the same chemical compound, right? So now what we're going to do is we're going to use our balanced equation, our coefficients, and put everything together, right? So in the land of givens, right, remember that molarities are conversion factors, so we're not going to start there, right? That means we're going to start here at our 27.2 mils. So we have 27.2 milliliters of nitric acid, aqueous, right? And then, before we can go anywhere else, obviously we're going to have to use that molarity, which again, if we rewrite that, that's the number of moles of HNO3 aqueous. Oh, nope, that's just the number of moles of HNO3 equal to 1 liter of HNO3 aqueous, right? So, now we're going to take our 1 liter of HNO3 aqueous, and we're going to tie that to our 0.135 moles of HNO3 aqueous. Okay, and then what do you notice? Yep, we should have converted that, right? So 10 to the 3rd mils of HNO3 to every 1 liter of HNO3, right? Now, those cancel, those cancel. We're at moles. Now we have to tie HNO3 to sodium carbonate, right? And we'll see here it's 2 to 1, right? So for every 2 moles of HNO3, we react with 1 mole of sodium carbonate. And I also know that for every 0.112 moles of sodium carbonate, that is equal to 1 liter of aqueous sodium carbonate. And then I just have to solve. And we get 0.01639, etc. liters of Na2, CO3, 3 sig figs is it, so 0.164 liters of sodium carbonate. Yes, as our final answer. And what that says is that we need, 16.4 liters of 0.112 molar sodium carbonate to react with 27.2 milliliters of 0.135 molar nitric acid. Yes, like that's what that math says with words, right? Now, if we take a look at our follow-up question, it says that a 25 ml sample of nitric acid solution requires this concentration of sodium carbonate what is the concentration of the HNO3 solution, right? So now we would like to solve for the concentration, which means that the molarity is actually our question, right? Molarity of my HNO3. And in order to solve for the molarity of HNO3, that means I'm going to need moles and liters, right? I already know the volume of that HNO3 solution, so really I have to solve for, right, we need to solve for moles. I'm given the volume. I know that this is 25 milliliters. I just need to figure out the moles. And I can do that using that information because, again, molarity is a conversion factor. This is going to be my given. All right, so now let's start with our 35.7 milliliters of sodium carbonate. And we're going to take our milliliters and convert that to liters. And then we're going to take our sodium carbonate, which is 0.108 moles of sodium carbonate for every 1 liter of sodium carbonate aqueous. Oh, no, we're not done. And then for every, if we go back to our equation, 1 mole of sodium carbonate, that reacts with 2 moles of HNO3, right? So this math tells us the number of moles that will react with that. And this equals 0.0077112 moles of HNO3, which then I'm going to divide by my volume, which is over here again, right? So 0.025 liters. And this is going to give us our molarity. Yes. Thank you for listening. Be good, and I will see you soon. And no worries, we will do lots and lots of practice. All right, be good. See you soon. Bye.